You are given a number written as a string and a target value t. You need to find the smallest number that's greater than or equal to your original number, contains no zero digits, and whose digits multiply together to give a product that's evenly divisible by t. If there's no way to satisfy all of that, you just return 1. Brute force checks numbers one by one forever. This trick answers in milliseconds. Hey, I'm Kai. Welcome to Fun with Learning Technology, where we build the thinking that gets you the answer, not just hand it to you. By the end of this one, you will spot this exact trap in seconds. Let's break down what we are actually being asked. Think of currency exchange. You never care about the physical coins, just how many of each you're holding. That's the whole trick here too. Count what matters, ignore the rest. This exact shape, digits meeting a divisibility target, shows up in interview digit DP rounds, batch scheduling systems, and number theory tooling. Learn it once here, and you'll recognize it everywhere. Digits meet divisibility. Here's exactly what we're asked. Given a length n and a target t, build the smallest n-digit number, no zero digits allowed, whose digits multiply together to something divisible by t. Take n equals 2, t equals 6. The answer is 16, since 1 times 6 is 6. This looks like it needs a giant search over every possible number. It really doesn't. We're only ever going to track 4 small counters. We're only ever going to track 4. Picture 4, labeled jars, 1 per prime factor. A tuple is just those 4 jars taped together into one object. A dict remembers which digit fills which jars. A set throws away any duplicate jar combination automatically, so we never track the same state twice. Floor division and modulo are how we count how full each jar gets from t. And join glues the final digits into one answer string. 4 familiar ideas, repurposed. You might think, just place the smallest digit that seems fine and fix things later. Watch this. N equals 2, t equals 16. Fly digit 1 first, it contributes nothing, and now the one slot left can't possibly reach 16. Digit 2 works because it leaves 8 for the last slot, and 2 times 8 is 16. So here's the tension, smallest first only works if you check the rest of the number, can still finish. Picking blind breaks. Here's the trick. The only way a digit can affect divisibility is through how many 2s, 3s, 5s, and 7s hide inside it. Digit 6 is really just 1 2 and 1 3 riding together. Digit 8 is really just 3 2s in a trench coat. So instead of thinking in digits, we think in 4 counters, how many 2s we still need, how many 3s we still need, how many 3s, 5s, and 7s. Those are the 4 counters from a minute ago. In short, every digit collapses down to one small 4-number vector. So we build what I call the reachability table. Start with 0 digits placed and all 4 counters at 0. Add 1 digit and track every new combination of counters that's now reachable. Add another digit, same thing. This is the same 4 counters again, just growing digit by digit. There's the pattern. The table grows fast at first, then stops growing entirely. Because once it can already hit our target, more digits just repeat old combinations. That's when we stop building it. Here's the plan in words before we touch code. First, factor t into our 4 counters, 2s, 3s, 5s, 7s. Second, build the reachability table up to n digits or until it stops growing, whichever comes first. Third, warp positions left to right and at each one try digits 1 through 9, smallest first, only keeping a digit if what's left can still finish the job. Fourth, if nothing ever finishes, the answer is impossible. We divide t by 2 as many times as it goes, then 3, then 5, then 7, counting each time. That count becomes our target tuple. If anything is left over after peeling off those 4 primes, no digit 1 through 9 can ever produce it, so we return -1 immediately. This is the impossible case handled in 3 lines. Rex is that digit to vector table from before, written as a dictionary. Cap trims any counter down the moment it hits the target, so we never track more than we need. Then we build reach 1 digit at a time, each new set built from every old combination plus every digit's vector. The moment a new layer matches the last one exactly, we stop. It's saturated and we fill the rest with copies. I used to let these counters grow uncapped, past the target. Total waste of memory, capping them the second we hit. Total waste of memory. Capping them the second we hit it keeps this table. Now we walk left to right. At each position we try digit 1, then 2 and so on and check whether the leftover need after subtracting that digits vector can still be finished by whatever digits are left. The first digit that passes gets kept and we move on. Smallest digit, check before it's committed. That's the whole reconstruction. That's the whole thing, start to finish. Factor t into 4 counters, build the reachability table until it stabilizes, then walk digits left to right taking the smallest one that still leaves a finishable suffix. 4 counters, 1 table, 1 greedy walk. Clean. The trickiest line is the covering check. For our n equals 2, t equals 6 example, at the last position we still need 1, 2 and 1, 3 with 0 digits left. Reach of 0 is just the empty combination, give us at least what does not cover that need, so digit 1 through 5 all fail there. Digit 1 through 5 all fail there. Digit 6 contributes exactly 1, 2 and 1, 3, dropping the need to all zeros and all zeros is trivially covered. In short, we are not looking for an exact match, we are asking does some reachable combination give us at least what's still missing. Let's run it. Position 1, we try digit 1 and check. Can the last remaining slot still deliver 1, 2 and 1, 3? Yes, digit 6 alone can. So digit 1 is kept. Position 2, need is still 1, 2 and 1, 3, but now 0 slots are left after this one. So digit 6, the only digit matching that exactly, gets picked. Final answer, 16. You could predict this by hand now. Pause here. What does this function return for n equals 1, t equals 11? Drop your exact guess, the actual return string, in the comments before I show the answer on the next slide. 11 is prime and it's not 2, 3, 5 or 7, so no digit 1 through 9 can ever contribute it. The function correctly returns -1. 2 mistakes people actually make here, forgetting that leftover factor check, so the code loops looking for something impossible and requiring an exact tuple match instead of a covering check, which throws away perfectly valid digits that overshoot the need. You could write this same idea as a recursive function with a cache, choose a digit, recurse on the rest, memoize by position and remaining need. It reads a little nicer on the page. Honestly, I think most people over-engineer this with a heavier recursive structure than they need, but for 200,000 digits, that's 200,000 digits, that's 200,000 deep recursion, and it knows the call stack. The iterative table wins here, that's the boring right call. Brute force scales with how many n-digit numbers exist, which for large n is a number with more digits than atoms worth worrying about. Our approach scales with n times the size of the reachability table. And because every counter is capped at the target, that table stays small no matter how big n gets. That's the whole payoff of counting exponents instead of numbers. If t is 1, the target is already all zeros, so the very first n-digit zero-free number works. If t has a prime factor outside 2, 3, 5, 7, we catch that immediately and return -1. And if n is too small for the counters to ever reach the target, even after the table saturates, the final membership check catches it and returns -1. Remember that brute force loop from the start, still running long after the video ends? Here's why we escaped it. Divisibility never cared about the actual number, only about how many 2s, 3s, 5s and 7s are hiding in its digits. Factor t into those 4 counters, turn every digit into its own small vector, build the reachability table once, then walk left to right taking the smallest digit, that still leaves things solvable. The portable takeaway: anytime a problem asks about a product's divisibility, stop thinking about the product's divisibility, start counting prime exponents instead. Want to take this further? The real version of this problem also has to search for the smallest number greater than or equal to a given starting number, which needs one more trick, matching digits tightly against that starting number. Say t has a huge prime factor, like 999983. Why does exponentiation by squaring not even blink at that? Pause and think it through. Take a second before I give it away. It's not factoring t repeatedly, it's squaring the reachability vector. So the cost only depends on how many times you double, not on how big that prime is. If two values of t reduce to the exact same prime power signature, do you need to solve them separately, or can one table entry serve both? Guess before I answer. One more second to think it over. The table is keyed on the prime power signature, so identical signatures share the same entry. That reuse is exactly what makes this scale to 200,000 digits.